Hi, this is a continuation of internal loading. We're talking about last time why internal loading is important, and each different points along the beam or member, they have different internal loadings. How do we find internal loading? That's our goal today for this video. So imagine if you have this 3D object here, and there are 4 external forces, F1, 2, 3, 4, they balance each other, and then you were asked to find internal loading at this section, okay? How do we do so? We're going to use method of section, which means we're going to cut it. We're going to cut here. When you cut it, you have 2 sections, right? You have top and bottom. Obviously, here we are choosing the bottom one. Of course, be aware you can do either one, top or bottom. So let's look at FBD for this bottom section. We still have the external forces, F1, F2. Then imagine if we don't have those internal forces here, this object, this section will not be at balance, right? So we are going to have some internal loadings, and those internal loadings going to balance those external forces F1 and F2. And using that equilibrium equation, that will help us to find internal loadings. So that's it for 3D. And now let's look at an example for, let's actually continue to look at the 3D here. So in terms of internal loading, and in this one here, you see the normal force N. N means normal. Normal is perpendicular to the surface. And then you have V. V is shear. Shear is parallel to the surface. In other words, it's going to be on the surface. Okay? So N, normal, being perpendicular, V being parallel. Then you also have a bending moment. You know, a moment, a torque to make it bend. So you have those three categories: normal, shear, and bending. Now let's look at the 2-dimensional. So this is a 2-dimensional, and we have 4 forces acting on it. And here, actually, I want to draw it on a note. So this is where I have started. So this is our 2D. We have F1, F2, F3, F4. They balance each other. So sum of forces equal to 0, as we learned in statics. Now, we had briefly touched about internal loading is have 3 categories. The first one is normal force, N. It has to be perpendicular to the cut. Okay. Then we also have our shear force. That's going to be, we call V. Shear force, that's going to be parallel to the cut. The third one is called bending moment. Bending moment, M. M is a torque or moment, so it's going to have a unit of what? Newton meter to make it bend. Okay. So imagine if you made a cut at this yellow line here, and you have left section and right section. If we were looking at FBD of the left section, then what do we have? We will exactly have this part. Okay. Then we have this yellow line, that's where we cut. Now we are going to draw all the forces acting on this left section. Do we still have F1, F2? Yes, we do. So we have F1 and F2. Then at this yellow section, we're going to have internal loading. There are three categories. The first one is what? Normal. Normal is perpendicular to the cut, so it's going to be this direction. Well, we're going to learn another concept. It's called the sign convention. When will normal force to be positive? The normal force to be positive is when it causes tension. So for example here, to make this left section to be tension and you have a force on the right that has to be going to this direction, right? So make a tension. Then for shear V, to make this sign convention to be positive, you're going to make it clockwise rotation. So you have this left section, you wanted this entire thing to go clockwise, and shear is parallel to the cut, which means it's going to be going up and down, right? To make this whole thing clockwise rotation, which direction do I have to go? That's right, to go downward to make this clockwise rotation. Then the last one, the bending moment. When will you make bending moment to be positive? This is my favorite one. It's to make a happy smile. So think about this. If you wanted this member to be making a happy smile, what would that look like? There will be, you know, something. If this bending is going to be like that, right? So to make a happy smile, this is where the yellow point is. And we're at right side here. So to make a happy smile, you have to apply the bending. This way. So in other words, I have to bend this way to make this happy, right? Make a happy smile. That's our bending moment. Okay, this might be easier to see if the structure is not a sphere shape. If it was like, for example, just like a member, normal member, and you do that, right? So you have normal to make a tension. You have shear going downward for this one to make it a clockwise rotation, and to make a smile. You see, that's easier to see. And we're on this side. To make a smile, this have to be going like this on this side. So make a smile that way, bending. Okay. So you have this set of three. You have normal, shear, and bending. That's for our FBD to the left. Now I'm going to try to use the same logic, same convention to do FBD to the right section. Okay. So for the right section, it's going to be something like this. And this is where we cut. And so for our FBD to the right, what forces are acting on this right section? Well, do we still have F3 and F4? Yes, we do. So we have F3 and F4. Imagine if we have no internal forces, F3 and F4 cannot balance each other, right? So internal forces have to be put into place to balance this section. Now let's take a look. Using our sign convention we're talking about here, normal is perpendicular, so it's going to be this direction. However, now the cut is on the left. To make this section to be in tension, so this have to be to the left for this situation. That's our positive. Then for shear, we're going to make this the entire right section to make a clockwise rotation. Shear have to be up and down, parallel to the cut. To make this clockwise, which way? That's right, we have to go up to make this clockwise rotation. That's our V. The last one is going to be our moment. Moment is going to make it happy. make a bending happily instead of pouting. We want a bending like this, right? If we're bending like this, we don't want to bend like that to be pouting. So in order to make a happy smile, and this is where we cut because it's on the left. So that moment will have to be this direction. So that's our M. So you can compare the FBD to the left and FBD to the right. And basically, they all have set of 3. However, the directions cancel out. Okay, that's all. So this is the internal bending concept. How do we draw internal loadings? At the next video, we'll show you using example how do we actually solve internal loading. Okay, bye now.